Okay, we are at the new Otani Hotel in Tokyo, Japan. It is June 22nd, 2016, and I'm Doug Fairbairn, and I'm here to interview Kunio Uchiyama. Yes? And so we want to explore your career in computers and electronics and software and semiconductor. And to begin, we'd actually like to hear a little bit about your life growing up, where you were born, what your family life was like, what kind of encouragement or lack thereof you might have had from your family or other relatives. And so if you would just begin with that, tell us a little bit about your life growing up and when and where you were born.
So my family there are two children, older sister and me, and my father was working for a trading company in Japan, and he was an accounting manager. And after his retirement, he ran his own accounting office.
So he never really retired. He just went from one business to another.
He worked till his death.
Did he work in the accounting office? Did he work for other small businesses, or how?
Just an accounting manager, accounting office. So he was checking the account of another company.
Okay. And he just kept working until he passed away. Is that right?
Yes. I think he spent a happy life.
He was happy working with numbers. And your mother's side?
Mother's side, she is a, how do I say, housewife, just housewife. And her uncles were engineers, all engineers. And my father was not interested in technology, science at all, but I think I was affected by mother's side.
Did your father encourage you to pursue any particular thing, or was just happy
nothing. He didn't care about me.
Okay.
It was okay.
Yeah. So, did you have any specific influence from your teachers or people that sort of steered you in a technical direction, or how did you develop your interest in technology? What were some of the things you did as a child?
Basically, I was good at science subjects, for example, mathematics and science. And when I was junior high school, I started to make crystal radio, vacuum radio, and transceiver. And I took a amateur radio license. And I was so excited about amateur radio communication.
Communicating with people around the world.
Yes, with my very poor English.
Did they teach English in school, or how did you learn English?
From junior high school in Japan, we have a class of English. But I think I got some English tape and tried to learn English conversation.
So you were teaching yourself. So you went through public schools from junior high school and high school?
Yes, they were public.
And then what university did you choose, and why did you choose that particular university?
I attended Tokyo Institute of Technology, and it is one of good universities on science and technology in Japan. that is one reason. And my childhood friend's father was a professor at that university. And the most important, there was no entrance examination on liberal arts, like Chinese classics, Japanese classics, Japanese history, world history. I didn't like to study them during my high school.
You preferred the sciences, the chemistry, physics, and mathematics?
Yes. I didn't like liberal arts at that time.
So, and the classes that you took there were all technical classes? You didn't have to take humanities, studying language or history or whatever once you entered?
You mean in high school?
No, once you entered the Tokyo Institute of Technology, did you take any classes in history or literature?
Yes, we could choose such kind of subject, but I didn't.
You didn't
choose. It was a mistake.
You wish you had in retrospect. So did you know from the beginning you wanted to study engineering, or did you study electrical engineering? Is that?
I entered information science department.
What year did you enter the Institute of Technology? What year?
It was just a moment. 1972. I entered TIT.
And so then you were studying information technology. Is that
from
right?
the second year. First year, that is a general.
Right.
And from the second year, we enter some department.
So then you pursued it through bachelor's, master's, and PhD. Is that correct?
Only bachelor's and master's.
Okay.
And in case of PhD, I got it later.
Okay.
During working time.
So your bachelor's and master's degree were in information technology?
Information science.
Information science?
Yes.
So did you learn computer programming?
Yes, I learned assembly program and Fortran at the time, and machine instruction. I was using tape. How do I say? Forward slash.
Tape?
How do I say? Tape. Tape or card reader.
Cards.
Yeah,
you were punching cards.
Yes, right.
Right. And you were programming in Fortran or in assembly language?
No, mainly assembly.
Mainly assembly
language.
Were the computers you were working with, were they Japanese computers or were they?
It was a Japanese computer. One is from NEC, and the other is from Fujitsu.
Did your work with computers get you interested in continuing to work with computers? Is that an area that you found very interesting?
I was in a university, I was not so interested in computer. So I chose applied mathematics for information theory.
Okay. So you have a technical, theoretical background in information theory. So you attained your master's degree in 1978?
Yes.
And then did you go to work for Hitachi immediately, or?
Yes, immediately.
And did you consider other companies, or why did you choose Hitachi?
Maybe my nephew was there. So I know the name of Hitachi.
Mm-hmm.
So I didn't consider deeply to choose companies, but I like some electric company.
Mm-hmm.
So I chose Hitachi by chance.
And when you chose the company, did you know what your job would be, or you just choose the company and then they tell you what they want you to work on?
Basically, I would like to become a researcher there. So when I enter the company, I told interviewers that I like to be in a laboratory.
So and is that what you did? You entered the Central Research Laboratory, is that
Yes,
correct?
yes.
So in your college work, did you learn anything about electronic design work or chip design or anything like that?
No,
or was it all
no,
mathematics and theory?
Just applied mathematics.
Okay. So when you entered the Central Research Laboratory, what were some of the first things that you were involved in? What was the first?
2 years, I was developing CAD software. It's a fault simulator. And I developed some algorithm for fault simulator.
So that was in 1978? Is that?
1978 to 1980.
And was that, so that was relatively leading edge technology. There was not good fault simulation technology available.
Yes, there was a big project to develop fault simulator in Hitachi.
And do you know what was driving that from a commercial point of view? Had there been problems, or they're worried about test coverage or whatever? Why had that become a big project at Hitachi?
Because at the time we were making chips and boards. That fault simulator was for checking a board, computer board.
Right.
So in order to keep reliability, checking fault coverage is very important.
Right. Do you know if there had been any programs in which there perhaps had been a major problem where, because of poor fault coverage, a product had some problems or whatever, or were they just trying to improve the quality overall?
Yes, we have to increase the fault coverage. In order to increase the fault coverage, we had to make good test patterns. It was very important.
Right. And so did your project help create the actual test vectors to give the appropriate fault coverage? Is that?
There are two teams. One is our team, that is for fault simulator team, and the other team is generating test patterns automatically. That was another team.
Right. So you identified where the problems were, and they worked on finding test patterns, which would then test for
we
those
collaborated
faults.
each other.
Right. Did you find that work interesting? Was that something that
it was interesting to develop a new algorithm.
And you had only programmed in Fortran or something before. What language were you using to program this?
At that time, I used assembly language of mainframe and also Fortran.
And so you were developing these, or running this fault simulation on some of the chips that were in design at Hitachi at the time, or
at that time that fault simulator is for board testing.
Okay.
So at the time, I think the integration of LSI is not is very low. Was very low. So we bought area size and put those on the board and test it.
Okay. So what was your next project or activity? What was
after that? I would like to design hardware. So I asked my boss to change my work from software to hardware. So it was easily accepted.
But you had never designed hardware before.
No. Yes. I like a new job.
And so what did you design, and what tools, and at what level did you do your design?
I made a logic design. And my target machine was small size mainframe computer.
So was this a project where there were many engineers working on it?
It was a very small team. And I joined one of the team. And I studied. At the time, I didn't know about computer hardware. So mainly I studied. And after that, we tried to make single chip, small size mainframe computer.
And so the architecture of the machine and the instruction set was defined, and you were...
Instruction set is compatible with IBM.
Okay. So you were designing a chip that would implement a predefined instruction set. And
so I designed microarchitecture, and I designed logic, and simulate them.
And was the simulation tools you were using, were those internal within
At that time, I
Hitachi?
think in-house logic simulator using mainframe. It was very slow.
So by this time it was the early 80s? You were
early 80s, yes. 82, maybe 82 or 3.
So that was very aggressive time to be trying to put a mainframe on a chip.
But precisely speaking, it was not one chip, maybe 2 or 3 chips.
And what technology were you targeting?
We were using 2-micron CMOS technology. It was in-house Hitachi's technology.
And were you able to get that chipset working to actually...
that project was stopped.
Before you actually made the chips?
Yeah. Just logic design.
So you at least learned the whole process of logic design and computer...
It was a
something
good
about
experience.
Something about computer architecture and so forth. So did that spark further interest in that area? What did you ask to be involved in after that?
After that, I belonged to a 32-bit microprocessor team. And we developed the Hitachi's first 32-bit microprocessor. And it was fabricated in the Central Research Laboratory's lab. And the chip was made, but it was not commercialized. It was just a prototype chip. The instruction set was original. It is like Motorola's 68,000.
68,000?
68,000. At the time, we licensed from Motorola.
So you said that that work helped Hitachi in the legal dispute with Motorola later on, is that
After
correct?
that, around 1999, there was a lawsuit between patent lawsuit between Motorola and Hitachi.
And how did your work help resolve that or help strengthen Hitachi's position?
As a when I was developing that microprocessor, I submitted the patent on memory management unit. It is related to content addressable memory. It was by chance, but that patent was used in the lawsuit.
So even though your chip did not get commercialized, you still had a very positive impact on Hitachi. That's good.
So there was 4 patents from Motorola and only one patent from Hitachi. That was my patent. And finally, the lawsuit was settled.
Did you just exchange patent licenses or
yes,
paid some money? Or?
Two sides. The judgment was infringement was we infringed each side patent each other. So stop commercialized microprocessor. But it was very damage on both sides. So we settled.
So you've now worked on a couple of different computer chip designs.
I made a lot of chip design.
So you said you had come back and gotten a PhD. Was your PhD related to your work in computer design then?
Yes, microprocessor design, low power microprocessor design. It was my doctoral degree's theme.
When did you actually get your PhD then?
PhD, it was when I was 47 years old.
So
it was 2001.
Okay. Yeah. So later.
Later.
So did you have to write a separate thesis to get the PhD, or did your work at Hitachi sort of qualify you for the degree?
I got the same. I did in the company.
So after you did the work on this 32-bit processor, you then took 1 year to go to the United States to do research at Carnegie Mellon. Is that correct?
Yes.
Tell me about that experience and what you learned there, how it might have influenced your later work.
I went to Carnegie Mellon University, and I belong to the laboratory of Professor H.T. Kun. And his team was developing systolic array processor. It was like a data flow chip, and to accelerate, I think, image recognition. It is the origin of autonomous driving.
Autonomous vehicle?
Yeah. Autonomous vehicle. They are testing autonomous vehicle, elementary autonomous vehicle on the campus. And we are developing the chip for image recognition.
So, were you doing actual chip design then, or
yes,
developing the architecture?
I designed part of systolic array using CAD tool. I forgot the name. It was a logician or like that.
Oh, Daisy Logician?
Yeah, Daisy Logician. Yes. I think I used it for logic design.
And this is during 1985 to 1986.
Yes.
Is that correct?
Mm.
And what was there? What did you find most interesting from both a sort of personal point of view and also a technical or career point of view about Carnegie Mellon? Maybe at first is just from a personal point of view, how did you find working there to be the same or different than working at a Japanese university?
I think first there were a variety of nationalities. Professor Kun, the origin is from Taiwan, and other people from Hong Kong. Monica Lam, she was a famous compiler, researcher.
Who was that?
Monica Lam.
Okay.
And other researchers, main researcher from France, and others from Germany, and so on, and Japanese.
Was there anybody else there at the time from Hitachi, or were you the only one?
Only me at the time, as a team.
So how was besides the different nationalities, what about from a technical point of view or other things? How did you find it different than doing research at Japanese?
I think it was a big team.
A big team?
A big team. And I think we couldn't see that kind of big team in Japanese university. Maybe 30 or 40 researchers there.
Yeah. All working on the same program?
Yes, same systolic array. And from hardware to software, compiler, and so on.
What about from a personal point of view? Did you enjoy your time there, and how did you find living in the United States versus life here?
In 1985, I just married. So I went with my wife. It's like a kind of a honeymoon, long honeymoon.
Was she happy being there in the United States?
I don't know.
You were working too much.
Not so much. I traveled a lot in the United States, and in summer vacation I went to Europe. We went to Europe. It was a good time.
So you enjoyed your time there. Did the work there influence your work in any clear or specific way when you returned to Hitachi?
I think I have to study more from the world. Not only Japan, but there are a lot of
learn about what else is going on.
Wide world in the world.
So. Before we go further, I'd like to sort of reflect back on the design work that you were doing, and one of the major issues that I'm sure came up in doing your processor design and chip design is whether to copy an existing instruction set and be software compatible, or create a new unique architecture and instruction set. And you said that early on you had done some work that was IBM compatible, and then some of the later work was compatible with the 68,000. But then later on you created your own architecture and instruction set, right? Can you tell me sort of what the driving forces and trade-offs were for those choices, and what role you played in sort of making the decision as to which path to take? Is that question clear?
I think original instruction set or architecture is possible, is important, because when we create new market, we customer's opinion is very important. And according to customer opinions, we redefine our architecture or instruction set sometimes. And
redefined it?
For adding instruction set and so on. And it's important, I think. So it's important to have original architecture.
So you had worked on this 32-bit processor before going to study at Carnegie Mellon, and that was one that was compatible or largely compatible with the 68,000 family from Motorola. When you came back, somebody chose to take a new path. Is that right? So tell me about that choice and what the goals of that were and how that came to be, the program that you were then involved in.
So after returning to Japan, there was a atmosphere to make original architecture or instruction set, Japanese original instruction set. That was a Tron project. And Professor Sakamura, who was in Keio University at the time, he proposed Tron instruction set, and we cooperate with him to make a new instruction set.
We meaning Hitachi?
Hitachi and Mitsubishi, Toshiba, Fujitsu, maybe main or Japanese company joined that Tron project and started to make their 32-bit microprocessor using Tron instruction set. And I belong to one of that project.
And what was the target market or application for Tron? Was it in computing or embedded processor or?
Basically computing or workstation or communication system and so on.
So it was meant to compete with the biggest processors from Intel or Motorola or whatever.
Yes,
is that right?
Right. So there was a Tron project that was an operating system.
Okay. So you were going to build the operating system, the processor.
Yeah, from operating software to
everything.
process. Yeah. But that action was failed, basically.
And why did it fail? What was the?
It's pressure from United States at that time. So we
from customers or from the government or what
maybe
of
from
pressure?
government, from the United States government. At that time, the power of Japanese semiconductor was very strong.
Yes.
And I think U.S. government was worrying about that.
Yes, it was.
So we tried to make Tron that was a operating system for business or education. It is like a Windows. But that project was stopped. I think by the pressure of United States.
How long did both the Tron and B-Tron were both stopped?
Yeah, B-Tron was stopped, but there was C-Tron. It was for communication. I think C-Tron was used in communication system. It is led by NTT. And the chip I developed was used in that communication system.
What was the what were the most important or unique characteristics of the Tron project? What you weren't trying to do just something that was different, but something that was better than what was already out there, right? So you wanted to. What was the biggest target you were competing against? Was it Intel's microprocessor family, Motorola?
Yes, we consider our competitors Intel's 86 or Motorola's 68 series and so on.
Right.
That was not embedded processor.
Correct. So, and where did you feel you could make a contribution? Where do you think you could make your program better than what was already available?
For example, it was that instruction set was CISC. But we developed a superscalar microarchitecture. And also very complicated branch prediction mechanism in the chip. I think those technologies were very latest at the time.
These are things that had been used in supercomputers or mainframe computers before, but not applied in the chip. Is that correct? Or had they? These are. Were these things that had never been applied in computing?
It's I think it's first time to apply those kind of technology in a chip. Our main designers of mainframe computer were usually conservative, so they didn't like very new, aggressive microarchitecture, I think.
So the Tron project, you think, was it just stopped? Was there a point at which you said no, we aren't
that was
going to do
not
this?
Stopped, but from the commercial point of view, it was not successful. Our chip was sold only to communication system. The volume was very low.
Now, obviously, you said that there was pressure from the United States. Were you able to develop a chip which met the original goals, or the reason for the lack of acceptance, was it mainly political or mainly technical, or a combination of the two?
I think the failure of Tron project was big, I think, because Tron is an operating system. If Tron was accepted, I think there was a huge market. It is like a personal computer.
So, you think the chip design itself was successful? You met your goals,
yes,
but without the operating system and so forth, then you couldn't really.
Circumstances around chip was problem.
So, how long did you work on the Tron program?
I think after returning to Japan, so 3 or 4 years.
From 87, you came back in 87?
Yeah.
So maybe until 1990 or so?
Yeah.
So what was the... so you've now worked on 3 major processor developments, right? And this is all in Central Research Laboratory, correct?
Yeah. Collaboration with not only Central Research Laboratory, but also another laboratories, and also, of course, Semiconductor Division. Usually, Semiconductor Division led all projects.
And so the division includes the laboratory as well as the product design people and so forth, and they work together to
Yes,
develop?
yes. We made a project, project team.
And was this the common way for at least Hitachi to work, was to combine people from different groups to work on a project team?
Yes, in Hitachi, there was a system to make a project from gathering from different divisions, laboratories, to develop an important chip and so on.
So you said there were many companies involved in the Tron project. Were there other teams developing other chips to implement the Tron instruction set, or was yours?
Yes. For example, Mitsubishi developed low-end Tron chip, and Fujitsu developed high-end Tron microprocessor, and Hitachi developed middle and high-end two microprocessors.
And were all of those chips completed?
Yeah, completed. They were commercialized, but they were not sold well.
Since you didn't have Tron, did you port Unix to the machine, or did you have C?
At that time, there wasn't Unix. I don't know where about that. I think Unix is not ported. Only in our microprocessor, Tron, that is a communication operating system, is ported by NTT.
So clearly, if you had a chip that was aimed at sort of workstations or general computing, it had to have an operating system working with it. Otherwise, it was not going to be successful.
No.
So you moved on from that project. What was the next thing you became involved in?
Next, from the beginning of 1990, at the time, digitalization of consumer products started. For example, digital camera, PDA, game console, television, and so on. So we discussed and we tried to make some new microprocessor for that application. So we changed our market from workstation or computer to embedded system for digital consumer.
And was that a new program that got kicked off at that time, or was that sort of redirecting something that was already going on?
It was not top down. It was bottom up. First, small start, I think.
What was the? Was there an existing processor that you, or instruction set that you focused on, or did you create a new architecture at that point?
We had there are several embedded type processors in semiconductor division, but the performance was low, so they couldn't satisfy the requirements of digital consumer appliances. So we have to make a more high performance microprocessor, but also low power.
So low power was a design goal from the beginning.
Yeah.
And what was that program? What processor first came out of that effort?
We made S8 Super H microprocessor. We call it SH, and it's a disk type. It has a disk type instruction set, and we optimize instruction set for digital consumer products.
Okay. So was the SH? It was 16-bit or 32-bit or what was
It's
it?
a 32-bit architecture, but the length of instruction set is 16-bit. It was very unique. So using 16-bit fixed instruction set, the size of program could be small. It was one of features.
Code size was very important.
Yes. At the time, code size was very important for embedded applications.
So was the SH program based on or extension of the H8? Wasn't there an 8-bit processor
No,
before?
it is different.
Totally different.
Totally different.
Okay.
We started from scratch.
Okay. And what influenced you to go towards a RISC type instruction set?
RISC. Because we believe that RISC type instruction set can make the chip size smaller compared with CISC, and cost effective, and also can get high performance.
So did you study the work that was being done at Stanford or MIPS or Spark or Berkeley or any?
Yes, at the time there are already in later 80s there were MIPS and Spark and so on. So we studied them. The problem was the length of instruction set. The length of instruction was 32-bit. So using 32-bit instruction set, 32-bit fixed length instruction, the code size increase. That was the problem. So we decided to adopt 16-bit fixed length instruction set.
Did you also look at the ARM architecture at the time, or was you not looking at that?
At that time, we didn't care about ARM so much.
Were you aware of it?
Of course, we knew it.
But that was not a... So there, you sort of like the RISC model, but none of the existing RISC processors really satisfied... None of them were a good model or a good example of the direction you wanted to take. Is that correct?
You mean
you didn't see in any of the existing ones something that says, okay, we want to build something like that. You saw maybe there was some inherent advantage in the RISC concept, but the implementations that existed at that time were not representative of what you wanted to do. Is that correct?
Because at the time, MIPS or Spark, they are for workstation.
Yes.
So they were pursuing high performance, basically.
Right.
So they were not suitable for embedded system.
So did you meet with those designers or with people from Berkeley or other places where they were doing research in this space, or did you?
No, I didn't see meet them. But I don't know other people met them or not.
So Hitachi started on a program to build a high-performance embedded processor that had high code density, high speed, and low power.
Yes, and low price.
And low price.
That is very important.
Right. So it had to be a small chip. It had to be able to go in a plastic package and
Yes.
all the other characteristics.
Natural cooling.
I'm sorry?
Natural cooling.
So
We don't put fan.
Pardon?
We don't put fan.
No
in
fan.
the system.
Had to
No
be
fan.
natural cooling.
Yeah.
Okay, so that program, when did you sort of fix the design goals and kick off the actual design program itself?
The first chip of SH was commercialized in 1992. It was used for digital camera.
So the development time was relatively short, it sounds like.
Yeah. Maybe 2 years.
And when you began the development, did you work with potential customers?
Yes, usually our development style was customer-oriented. So we discussed with customers about specifications of chip. That was very important.
So what companies did you work with for the digital camera application?
Digital camera application, that was a camera from Casio.
Okay.
It was very successful using our chip.
And
I think that camera was the first successful digital camera in the world. The resolution was very low comparing with today's. It was only 250,000 pixels.
Yeah. Did Hitachi have a good long-term relationship with Casio? Was that?
Yeah, Casio was a good customer of Hitachi Semiconductor Division.
Did Hitachi also develop other parts of the camera, like the image sensor or other elements?
Yes, we tried to make image sensor also, but I think our image sensor was not successful. There are more strong image sensor makers.
So your major contribution was on the SH processor. So did you develop a special operating system for use in embedded products to go with the
operating system? I don't know the operating system, but just there was an operating system called Tron. That is part of Tron project.
So it was spun out of the...
Yes, Tron is for embedded operating system.
So
very tiny operating system.
Right. Right. So that was the first product was very successful. Were you designing multiple chips, or the first goal was to get a single chip out and then build on that to get higher performance or whatever?
I think it was a single chip solution. So it includes CPU and memory on a chip.
And what were the next applications that you were able to address with that chip?
Next chip, based on that SH1 design, we developed a microprocessor for a game console. That was Sega's game console. The name was Sega Saturn.
Saturn?
Yes. We developed SH2 for that game console. It was very successful at the time. So it was 1994 or 3.
And by this time, I forget, had ARM emerged as a competitive embedded product at that time?
Not yet.
Okay.
So 1994 and 1995, the shipment of SH was SH achieved number one share
Mm-hmm.
in disk processor market.
Mm-hmm. Oh,
Yeah, I think.
big
Because
volume.
Of, yeah, because
Mhm.
of game machine.
Mm-hmm. So, forget what I was going to ask. Okay, so you now had a very successful product. You must have felt very good. The previous chips you had worked on were not commercially successful, but now you had a product that was doing very well. It sounds like.
Yes.
So it sounds like that was a pretty unique product on the market at that time. If ARM had not yet sort of emerged, there were not Intel and Motorola were not pursuing that market either, right?
But MIPS tried to enter that market.
That's right. MIPS did go after an embedded.
Yeah, and also PowerPC after that.
Uh-huh.
And also Japanese NEC, they had a embedded disk type microprocessor.
Your product must have been much lower power than these other products, though. Is that correct?
Yes, we are pursuing performance powered figure or MIPS powered. We try to achieve number one position at that figure.
So you continued to create new generations of the SH processor in new semiconductor technologies, but also spinning off different chips to target different markets. Is that correct?
Yes. And after SH2, we developed SH3. That representative product, customer product was PDA, personal digital assistant.
Did you continue to be personally involved in all of these programs?
Oh yes.
And what was where did you focus your efforts? Defining new chips or doing design, or what was your...
defining chip and lead the development team. And achieve the performance powered and so.
What did you... Were you addressing the power performance at sort of all levels, both the architecture as well as the detailed design level, sort of minimizing power at every step? Is that the way you approached it?
We developed a variety of techniques to minimize power and also achieve high performance. So it's there are a lot of efforts.
And at some point, looks like you pursued one that was focused on digital signal processing, DSP.
Oh yes.
Tell me about that program and what the goals of that was.
We have an original DSP, but it was not successful, I think. So
a single chip processor.
Yeah, single chip. Yeah, only DSP chip.
Yeah.
So I think a manager of semiconductor division considered that the DSP architecture should be merged to SH because SH was successful at the time. So we defined SH DSP. We merged DSP instruction set to original SH instruction set.
So you put in special hardware to enhance the performance for certain DSP applications. Is that correct?
Yes, we are trying to that DSP SH DSP for baseband application, baseband processing application for a mobile phone and so on.
Did you also target the handset market as well, or was it not suitable for that?
So handset means
Actually, in the phone itself.
oh, phone itself. Yes, I think so. So I think that architecture instruction set was suitable for processing handset application.
So were you able to penetrate that part of the market? Did you?
Other team, there was another team for SHDSP, was SH3DSP.
Okay. So they were spinning off different.
Yeah.
So does that? So does the SH processor development continue now, or has that been spun off in Renesas, or?
Spin off to Renesas.
So when it was spun off, when did Renesas? When did that?
The Renesas was created in 2003. So all semiconductor division in Hitachi went to Renesas.
So did you go with that, or did you stay with Hitachi?
I stayed in Hitachi, but some colleagues went to Renesas. And we are now we are also collaborating with them sometimes.
So until it was spun off, was your major focus on continuing enhancement of the SH processor?
Yes.
Is that the major focus of your work?
We are we are collaborating with them. For example, we developed SH Mobile with them.
I see.
It is for application processor for a mobile phone.
So you're still part of the Central Research Laboratory?
Yeah.
But so you continue to work on the SH processor even after it was spun out. Is that correct?
Now, I'm not involved in it.
Okay.
But maybe till 2010, I collaborated with them.
So for several years, 5 or 7 years afterwards, it was. So you were. So you worked on the SH processor for a long time, from 1990 to 2010, for 20 years.
Too long.
Too long.
Yeah.
So after you sort of stopped doing that, what was the next program you got involved in?
After the mid 2000, around 2004 and 2005, I started a multi-core project. It is kind of a national project.
Multi-processor?
Yeah, multi-processor. Multi CPUs on the chip. And I carried out 3 projects related on heterogeneous multi-core. So, and we cooperate. I cooperated with Renesas Technology and universities.
So that was a very important area. That people were not able to continue to increase the clock speed of the processors, right?
Yes.
What, mainly because of the power problem, is that correct? So you were looking for ways to increase the performance of the processors by doing multiple cores. And so what was the focus of that work? Were you mainly looking at sort of general purpose computing applications, or were you also thinking about even embedded kinds of applications for these multi-core projects? What was the...
That is for embedded system.
Okay.
Very advanced embedded system, like cell phone, smartphone, and advanced digital consumer. And also autonomous driving.
Okay.
It needs a lot of computing performance.
Right.
Mm.
So were there particular customers that you were working with to help define what the...
But there were no customers.
No customers.
That's a fundamental technology project.
Right.
So we just developed prototype chips.
Mm-hmm.
We made 3 prototype chips
Mm-hmm.
using heterogeneous multi-core architecture.
And what were the differences between those?
Mm.
What different things were you exploring?
The first thing we improved a little for each processor. The
Mhm.
first chip was there was 4 CPUs
Mm-hmm.
and two accelerators.
Mm-hmm.
That was the architecture was heterogeneous.
Mm-hmm.
And the second chip was 8 CPU cores.
Mm-hmm.
CPUs were SH.
Okay.
And we developed not only CPU but also the chip but also parallelizing compiler.
It's as big of a software problem as a hardware problem, right? To figure out how to take a task and divide it between multiple processors.
Yes. So Waseda University has a specialty of parallelizing compiler.
Mm-hmm.
So they developed it.
Mm-hmm. And did that parallelizing compiler, did it apply to any application? I mean, could you take any program and run it through this?
It can apply any applications if the application is written by Fortran or C program.
Mm-hmm.
Only language limitation.
So, still writing in Fortran after all this time, I thought.
But in a supercomputer area or high-end simulation, they are still using Fortran.
I didn't realize that.
Yeah.
So what kind of performance, if you have 4 processors or 8 processors, what was the typical performance gain? You couldn't get 8x with 8 processors. You got something less than the number of processors, correct?
But in our case, we can get, for example, x8 times, 8 times using 8 CPU cores.
Oh, you could?
Automatically.
For certain applications. Some applications were more
or less.
Were easier to get performance. Others were more difficult.
Right? Yes, of course. It depends on applications.
Right. So the things where that you have image processing or algorithms that could be done in parallel, then the multiple processors was very powerful. Is that correct?
Yes. For example, image processing, they have inherently parallelism in their algorithm.
So there are many other companies trying to do the same thing. Intel has multiple processors.
Yes.
Oracle has multiple processors. Everybody doing processors is trying to figure. Did you work with anybody else? Was there any cooperative program with anybody, or either in Japan or in other parts of the world? What was your, or were you working mainly just
we have
Hitachi?
In cooperative with Renesas, of course, Renesas Technology.
Yes.
And also National Laboratory.
So mainly in Japan.
Mainly in Japan, yeah.
You kept track of what other people were doing, but so did you feel that you had some unique technology that was better than what you saw in terms of your competition?
Basically, our target is embedded system. I think the promising application is autonomous driving. They need a very huge power, but power consumption is limited.
Right.
So we are trying to pursue that application.
What other companies are pursuing the same application?
A lot of companies, I think. Autonomous driving is a very hot topic.
Yes.
these
What
days.
other semiconductor or chip companies are trying
For
to develop a
example,
similar product?
NVIDIA.
NVIDIA.
They're trying to make a chip for autonomous driving.
Mm-hmm.
And of course, main semiconductor company, of course, Renesas and other semiconductor companies are trying to make chip for that application, I think.
Mm-hmm. It's a long payoff. It'd be quite some time before you have volume in this area. Is there? What about if you had more processors, 16 or 32? Could you continue to scale the performance with that, or do you reach some plateau?
Oh, yes. I think my recent interest is when Moore's law ends.
Is what?
Moore's law? Do you know Moore's law?
No.
No, it's a semiconductor law. Moore's law.
Moore's law?
Moore's law.
Oh, Moore's law.
Moore's
okay.
law.
Yes. I'm sorry.
I think it will end around 2025.
Yes.
So maybe the number of cores can be implemented on the chip will be stopped.
But if you could put 32 cores on a chip, could you get 32 times the performance, or how?
Oh, I see. I think the architecture become heterogeneous. Not only CPU but also accelerators.
Okay.
I think the role of accelerator is very important.
Right.
CPU is not efficient for example, image processing. So in that special application, we need excellent accelerator.
So are you doing research in that area as well, and like image processing accelerator?
I used to be doing that, but now I'm just watching the trend.
I presume NVIDIA is very focused on that.
Oh, yes.
And what do you think the other important trends for complex processors is? There's multiple cores and then accelerators. Are there other things that you're looking at?
Other things are, for example, three-dimensional stacking of chips. I think that is mandatory after beyond Moore's law.
So, these are the areas that you're currently active in today. Is that correct? Looking at all of these new technologies and helping.
Yeah.
Is there anything that you've been involved in, or that you're currently involved in, that is beyond what we've talked about? Are there other things you'd like to tell us about?
No, we are. I'm carrying out a small collaboration project with university.
So you're now so previously you were involved in actually product design, and now you're involved in more long-term research and looking at future trends and that kind of thing,
yes,
right?
And new applications and so on.
What is the optimum number of processors cores per chip today? Is it 4 or 8? Is that
recently, for example, using 16 nanometer technology, we can find the chip. There are 15 cores on the chip. So the number is a lot.
Then you have to have the software to keep all of them busy at the same
Yeah,
time.
yes,
Yeah?
software problem is very big, I think.
Yes. Okay, is there anything else you'd like to conclude or discuss? Or have we covered all of the important things?
I'm very glad to have this interview.
Okay,
Thank you very much.
Thank you very much. Appreciate your taking the time to do that.
Thank you.